In a previous video, we looked at how to code up the acceleration decomposition in Mathematica, and we looked at an example where the curvature of a circle is 1 over the radius of that circle. In the Mathematica demos for Calculus 3, we've got a lot of demos run. We can see that there is a demo called T and N frame curvature oscillating circle for plane curve. Got a little demo set up here that if we were to put in specifically a circle of radius 4 and we were to run this code, that I've got the different calculations for the position, velocity, acceleration, the t and n vectors, and then the curvature formula done kind of all nice and organized for us. Okay, so here we can see for a circle of radius 4 that the curvature is 1 over 4 or 0.25. Okay, and so one thing we'd like to see here is not only can you see the computations that are involved, but you can also see a plot. And here if we zoom out, we should see a circle of radius 4, right? And we can see the t and n vectors. In this case, they are the black vector is pointing in the direction of t. The red vector is pointing in the direction of the unit normal, okay? And the normal component of acceleration is 4, the radius. So this acceleration vector is this red object right here, and it's 4 times as long as the unit normal vector. Okay, so one thing we want to do is talk about curvature in terms of the radius of the curvature of this circle. So here we can see that the radius of this circle is 4, and we're going to say the curvature of this circle is 1 over the radius, which is a fourth. Okay, if you increase the radius, let's go to maybe 8. If you increase the radius of this circle, we should see the curvature, of course, be this 1 over the radius, and therefore the curvature is going to be a number that is smaller than 1/4 because the radius got bigger. So a circle of large radius, it has a small curvature. Okay, now this is the essence of the curvature formula when the curve is not a circle. So in one of the last videos we did the formulas for the t and n computations for a parabola. So here is the computations for that parabola. Okay, we did all of these by hand, but I've written this little program that organizes them for us all nice and neat and pretty. So we have the position, velocity, acceleration, t and n, and then the curvature formula is this pretty complicated looking formula. Now what is the meaning of this curvature formula? It really helps if we look at a plot, for example, first of this parabola. So you can see here we have the equation of a parabola, right? Typical equation of a parabola. Now look here, there is a circle right here that this circle, this circle you can see perfectly matches with the function at the vertex of the parabola. Can you see how the circle is curving and bending to nicely match up with the parabola at this point, this red dot at the bottom here? Okay, so sorry, let me show you the mouse over. Here we go. I believe oh, I was trying to show you the mouse. Let me make sure. It should be going. There it is. So right here at this point, we got the circle being drawn at this point, and there's a circle that nicely matches up. Now, if you look at the radius of that circle, the radius of this circle, if you could get out a ruler and measure it, and take 1 over that radius, that's what we're going to call the curvature of the curve at that point. Okay. If you move the point a little bit, notice what's happening, that the circle right, is getting to be a bigger radius. Okay, the larger the radius, in this case the radius is 1.33188. If you take 1 over that, the curvature is 0.75, which is a smaller number than the curvature was at this point. The curvature here is a number around 1.9 or 2, and the curvature is dropping and dropping and dropping because the radius of this circle is getting bigger. The radius of the circle is having to get bigger so that it can match up better with the curve, the black curve at this point right here. So as the curve gets flatter, you can see the parabola is kind of leveling out. It's getting more straight. As you get to those points on the parabola over here, you can see that the circle has to be really, really large. Right? So I can zoom out and you can see how large of a radius this circle is going to be. Let me see if I can go a little bit further. So there's our circle. And that circle has to be large because the curve is flattening out at that point. So the larger the radius of the circle, the smaller the curvature is going to be, which is kind of matching your intuition. A small curvature means that the curve is not bending very much. Okay, so if you were to move to a much flatter part of the parabola, the circle is quite big, so big that it's going off of the screen. Okay, so this is a mechanical way that what you can do to find the curvature, and that is to basically look at your curve and try to draw a circle that nicely matches the function. This is called the tangent circle or the osculating circle. It's like the tangent line, except it's a circle that matches up, a circle that curves to match the function. Okay, so the curvature at a point over here, for example, if you wanted to know the curvature of the curve at that point, you draw a circle that you think fits it, you measure the radius of that circle, and then you take 1 over the radius of that circle, and that would be the curvature of the curve at that point. Now we've done a really cool thing with our curvature computations. The normal component of acceleration divided by the speed squared. That comes up with a formula. Let me see if I can make this so I can get both of these plots on the screen at the same time. If you did the normal component of acceleration divided by the speed squared, you get a function, right? Here is the plot of that function, okay? Now if we start moving the point around, right, we can see that the maximum curvature occurs right here, which is at the vertex. That's because the oscillating circle, this tangent circle, has a radius of 1/2, and therefore 1 over 1/2 is a curvature of 2. So this curvature function is keeping track of the 1 over the radius of the oscillating circles at every point. So if we were to move points, right, you can see that the circle is getting larger and larger, and therefore the curvature is lessening and lessening and lessening until the curvature gets so large that the radius of the circle gets so large that the curvature starts dropping to 0. So this is an interesting way of basically saying that the parabola, as you get farther out on the parabola, it gets flatter and flatter, and essentially looks like, is starting to look more like a straight line. Okay, but near the vertex, this is where the curve is so curved, the maximum curvature is 2 here. So right here at the vertex, this is where the tightest turn is happening. That's your point of most curvature right at this point. Okay. Now this is, once you have this code and you have all the computations that we've done in a previous video, you can start to look at interesting functions. Parabola is interesting, but maybe not the most interesting that you're interested, maybe not the most interesting to you. But this is an interesting formula in the, 2.1. So I've been having a little trouble with this code. Sometimes I can look at another one. Let me see. TNN plot. Yeah. Let me just pause this and find the right. All right, they're computers, so computers are going to have bugs in the code, some of the code I wrote. But I changed the numbers in front of the cosine and sine to be 2.1 and 3.2. And what you can see there, if we zoom out, we should get the formula or the equation of an ellipse. Okay, so here is our ellipse forming. Just trying to zoom out enough where we can kind of see all the relevant features. So there's the oscillating circle, and if we increase the plot time, we can now see the whole ellipse. Okay. Now, according to our computations here, at this point on the ellipse, right, there is a circle that nicely fits that ellipse at that point, and that circle is of radius 4.87577. Okay, so the curvature is 1 over that number, or 0.2. Okay, as you start to move the plot, right, we can see here that the circle is getting smaller and smaller, which means that the curve is getting more curved. Okay, and right here, that seems to be the smallest the circle is going to be, right? At this this apogee or perigee, I can't remember which one, but at this top point of the ellipse, and therefore this is the point of most curvature. And as you progress a little bit more, the circles are getting larger in radius, so the curvature is decreasing until we get to be the biggest it's going to be at this point, and then actually it gets more and more curved in this direction. Okay. So if you want to see the computations that are going on there, you can look at the curvature formula. You can run through. Sorry, let me image size. Let me make this a little bit smaller so we can see what's going on here. And then, okay. Now let's take a look at what we've got. Right here, this is the point of smallest curvature. That's the biggest the circle is going to be. Right? And as the circle gets smaller and smaller, the radius is increasing until you get to a maximum at that farthest point. The curvature is getting smaller and smaller until we get back to this point where the circle is largest, and then the problem keeps continuing in this sinusoidal fashion. So we go from point of maximum curvature. The curvature is decreasing. This is the smallest the curvature is going to be. That's the flattest part of the curve. Curvature starts to build up again until we reach our maximum. Okay. And the cool thing is you can code all the formulas by hand for T and N and all that kind of stuff. But here are the computations that are done. We've got the position of the curve, the velocity, the acceleration. We found the unit tangent, unit normal vectors. To find the curvature, it's the normal component of acceleration divided by the speed squared. And this formula right here is what we are seeing in the plot right here, this term with sines and cosines in it. Right. All right, so ends just an introductory look at the idea of curvature. If you're interested in more of this idea, that there's a whole subject called differential geometry about this this curvature idea, and Calculus 3 is a good beginning point for that subject.